from the point of view of an RI seminar, this is going to be really excellent. But as you know, I'm also interested, in addition to looking forward, in looking back and sort of trying to keep track of our history, save the robots from the oncoming hordes and whatnot. And let me tell you how all this happened. We have the Girls of Steel to thank because they're getting a practice arena in one of the CMU warehouses. So they had to get all the junk out. And Gene got a phone call. They said, oh, it looks like you got a robot here. And Gene said, throw it out. And I heard about that. I said, oh, that'll save everything. You know, we have a lot of alumni here. They're going to want to know, what's the difference between now and, say, 5 years ago, 10 years ago? The answer is, Atkinson has put more crap in the hallway. Okay. Gene back yet? Okay. So we did rescue the robot. I want to thank Tim and Chuck for, you know, you can tell the difference between the sort of novices and the experts. The novices look at the robot and say, wow, that's really cool. The experts look at the steel frame they welded and say, whoa, that's really cool. Okay. I want to acknowledge a personal debt to Harry Asada. So, I was a young whippersnapper at the MIT iLab, and totally theoretical. We were doing all these equations of robot dynamics and, you know, blah, blah, blah. And Harry came up with the idea, let's build a direct drive arm here at CMU, and that saved me, that allowed me to do my thesis, because the thing about a direct drive arm is you can sort of accurately generate torques in the joints and measure them. Okay? So, wow, I was saved. He also taught me a fundamental lesson, and that is paint your robots fire engine red. Okay? He also taught me another fundamental lesson, which is do crazy stuff. So there you go, Harry Asada.
Well, good morning. Thank you, Chris, and for a wonderful and very kind introductions. This is really exciting. Thank you for inviting me to the seminar here on the day of the 40th anniversary of Robotics Institute at the CMU. I spent the first 18 months of my U.S. career in here in Carnegie Mellon back 1980 or somewhere. And I had a wonderful, the most exciting experience in that because I interacted with the really brilliant people who I would say that they actually they made the history of robotics. I think you agree to that. Takeo Kanade was my direct collaborator. I learned a lot from the Takeo. And a little after me, Mark Rabert joined in a team. And by that, already Arthur Sanderson and Paul Wright already there. And then Matt Mason they came in. Matt and me were traded. Me traded out to MIT, and he was traded in to CMU. So kind of steer as patriots, the trade and it happened, and both sides are very happy after that. But anyway, it was very important for me that I worked in such a stimulating, exciting environment and interacting with the world-class people. So this is what Chris found in the warehouse, the labeled as the CMU DD Arm. And 40 years ago, no one believed in the direct drives. But it's very important to say that at that time I was just visiting research scientist from Kyoto University. And it is very unusual that the visiting research scientist like me was allowed to build such expensive direct drive arm. And Raj financed, and Takeo convinced Raj, and we built this guy. It's a really crazy machine. So I got the sense that the CMU Robotics Institute had the full of innovation spirit, and which is very important. This turns out to be the world-class leader in the robotics and research, and ever since, almost 40 years. Before joining a CMU, I got a couple of little articles, just a small articles in the magazine. One said the Sumerian cobalt, rare earth magnet, just came out in the late 70s with the BH maximum of 48 megagauss Elsted. This is actually game-changing, big quantum leap compared to ferrite magnets. And nowadays you have better ones, but at that time it was really game-changing and a big technology advance. The other part is power electronics. Late the 70s, high power MOS FET just came out, and that's available and to drive the big current. And these two technologies are key things to make that direct drive possible. Well, after that, direct drive was actually commercialized by Adept Technologies, and Adept one time they dominated the market, but it's a little expensive, so they were replaced by cheap scatter robots. This guy? Oh yeah, okay. But one particular area that's actually wafer handling and clean room, it's exclusively by the direct drive robots like Brooks Automations, and here they can achieve the less than 20 micron absolute position accuracy, and more importantly, no gearing, so no particles coming out. And it's easy to put the kind of suction inside this in the body, and that makes this one almost perfectly clean robot. Direct drive has a renewed interest when Dan Kodicek built the Rex robot. They went to direct drive because direct drive can better handle the kind of rough terrain. So putting it there, you have to absorb the kind of impact from the floor. You can do that very well. Later, my younger colleague at MIT, Sanbei Kim, used the near direct drive type of motors to power these legs. In fact, almost 40 years ago, I attempted to convince Mark Raybert that the direct drive is the way to go. But Mark is Mark, you know that, right? And he did a great job. But in fact, almost 30 years later, the Sanbei Kim did it. And so that's a story. Now, this talk, I will not talk about only old story, but taking the same spirit of innovations, I'd like to talk about the two major areas that I have been working on in the past less than 10 years. One is Bionics, and where we use the living cells as a component for building robots. And the other side is wearable robotics, specifically supernumerary robotic limbs. And when you hear the biobot, the bionics and like this, it sounds a crazy science. But someone told me, perhaps Takeo, someone told me that it sounds crazy now, but 10 years, 15 years, and 20 years later, it becomes a standard. And so we hope that is to happen. My lab at MIT, one side is actually in a cell culture room, bio-wet and engineering. The other side is dry engineering, and we do robotics, wearable robotics in particular. Today, I focus on mostly this part. For this audience, this may be more appropriate, the topics. So let me start with the supernumerary robotic limbs. That you have third arm and the fourth arm, or the third leg and the fourth legs, or you have 7 fingers in one hand. So these are the additional limbs attached to your body. When I came up with this idea, we tried to find some words which never been used in the robotics literature. And the supernumerary, sometimes people use in the biomechanics literature that never been happened. So, non-native speakers of English, they have to look at the dictionary. So that's the way I found this word. So if you hear it once, never forgot. But it turns out the supernumerary, this is hard to pronounce it if you have to pronounce it correctly 100 times every day for research and conversation. You got lost. So we just simplified the SuperLimbs. So for today, we call it the SuperLimb. SuperLimb is one unique type of wearable robots. The exoskeletons and prosthetics. This is to compensate for the lost functionality. This one is to empower the existing joint here. On the other hand, the SuperLimbs is actually extra limbs that's not going along the kinematic structure of the human, but it's coming out. We can use it freely. So it actually comes up the many interesting stuff. So basic design concept came from the real needs, and shown here is final assembly of aircraft. It's all based on manual labor. And the people here working, on the ceilings, or floor, because the ceilings the whole day, long. They got a lot of troubles, and as you try to take this kind of postures, for many hours, you get trouble. Our solution is to put the robots on the shoulder, and that goes to this design.
At the Massachusetts Institute of Technology, robotics researchers are developing ways to add an extra pair of arms to your body.
The robot will try to act according to what I'm doing.
Robotic arms come to life thanks to artificial intelligence. The AI system monitors the wearer's arm movements, and eye trackers detect where the person is looking. From this data, it predicts the next movement of the wearer and automatically moves the robotic arms to a supporting position. No explicit human input is needed. The more you use the device, the more accurate the movements become as the AI system learns the way the wearer moves. The next area of research, adding extra fingers. Wearable robotics are extending the physical capability of human beings.
It is difficult to achieve comprehensive decision.
So there are many interesting ways of using this, not only this part. So shown here is some hard work you have to do on the ground. You can see the similar situations in constructions or, agriculture, gardening. You have to take that hard posture for a long time. If you continue that for a long time, you get the troubles with the lower back and the shoulders and the necks and the knees. You have to extend your body to take the ergonomic posture, but you have to reach the ground. So you have to lean forward. Then you need the support that result in the concept of a mantis bot. The body is braced by extra limbs, and here, and just like praying mantis, freeing the two arms, for eating something. So this one, no harmful strain concentrations along the spine, and both hands are free for use, not used for just bracing its own body, free to use. And in addition to that, those are servoed joints, and we implemented the impedance control. So the body is actually suspended with the desired tuned impedance and stiffness damping. So you can, free to move. You can see the fundamental difference from exoskeletons. Well, exoskeleton is basically, empowered, strengthened the joint, strengths. But if you apply this one to this kind of work, working on the ground, you find that the human body is not designed for doing the floor job. This is kinematically wrong configurations. So even though you strengthen the joint, it doesn't help very much. So you have to change the structure that goes to SuperLimb. So as you see in this case, floor work, and they have to take this posture for a long time. So we tested this one.
Simulated motions and.
So this is a Boeing 767 cargo space. You really have to reach in here and take this posture all day long. So there are interesting applications areas. We started with many different designs, but the challenge is communication and control. Unlike the exoskeletons, there's a case just to follow the natural, legs and arms configurations, and you just extended their strengths. But SuperLimbs, you can take any postures, so you have more opportunity to more freedom. However, you need more controls and communications, and controls a major challenge. So we worked on this, quite intensively. One type of a control is a spontaneous, independent control that you want to express your intention to the robot and putting some sensor here, right? The other side is actually reducing the workload for the humans, so maybe autonomous controls. The robot has its own sensors and closed loop. However, don't forget that this robot is attached to the human body and have to work in concert with the humans. And if the robot does the job in its own way, it's out of control. It's not the kind of stuff that you want. So, in somewhat, how you guarantee the, assure the kind of coordinations with the, the humans. So one particular mode is so-called the leader-follower control. And then we extended to bio-artificial synergies, and let me explain this. So simply, the previous example, robots on the shoulder, we actually did some, kind of the teaching by demonstration, the method. This, seating panel work has been done by 2 workers. Here's the leaders and the followers. At this time, followers basically support these leaders, but at this time, holding this backdrivable, robots, and show the kind of posture that this robot should take. And we take a measurement of both leaders and arm motions and posture motions and the joint displacement of these. Then they get the data and extract the coordination predictor to predict from the human behavior to robot actions, and that is transferred to the robot. So you take the some time sequence data, Basically, we have many measurements, and set this time windows. So we get the 360 dimensional input space, taken from the human leader motions, mapped to predict the 8 DOF robot motions. So this measure the output is actually an output data to predict, and we put it into data matrix and do some partial least squared analysis. And this guy, basically, we do singular value decompositions of cross covariance matrix between input and output, and pick the first most critical component, the second one, the third one, just like a principal components. And first few components explains almost 90% of the data. So this is the first mode. As you move this, robot reacted to this. This is what you did in teaching by showing the demonstration. And this is interesting. The mode 3 is kind of unexpected mode that you move this robot reacted to that one. So we basically simplified the high dimensional stuff. And then we, in fact, at the end of the day, we need to basically, measure only 3 components. So, and then each of them are going to 3 modes. And these modes are called the synergies in biomechanics motor control literature. And brain does not control the individual muscles, but instead the brain is to control the group of muscles as shown by the eigenvectors, and I would say. So just the 3 components allows you to do that. So as he move up, this guide robot reacts to it, and as he moves, taking that measurement, and the robot evoke what things are done before, and move to our next section. Well, same thing we applied to grasp postures, and it is known that the 5 fingers are not moving independently, but according to Santero's experiment, he actually took the finger joint angles, 19 joint, when human subject try to pick the eggs, toothbrush, and so forth. They actually get some data, and doing the principal component analysis. First, the 2 components, one actually, open and close, in phase. The other is kind of twisting and stuff. These 2 modes explained in more than 85% of the data. Now, we have 2 extra fingers, so we try to extend it, and whether or not such synergies among 7 fingers exist. We ask the human subject to grab these parts, and also manually control these 2 robotic fingers to the desired locations. We analyzed the data, and then we found that first the principal components explain the 65% of the data, and just 2 or 3 components almost completely explain the covariance data. And actually, here's the mode 1 to 3 involved in it. But our case is not just finding the synergies, but we like to control these 2 the finger robotic fingers in concert with the natural hand. So again, this as an input, this is the output, and we reformulate it, and the data matrix split it into 2, and we apply the partial least squares, which is a little bit different from the standard principal component. So this is the first mode, and this is the second mode, and you can combine these 2. So again, that we have many degrees of freedom, but humans does not, and central nervous system does not control individual muscles, but group them together, right? So as if the nervous systems extend to these fingers, if that is the case, what is the behavior you would see? Although we don't have the nervous system here, but it looks like that it's actually extended to this. Now, this work is actually primarily for assisting a hemiplegic patient. So one side of the arm is not actually usable. So they appreciate, if the one hand can hold and manipulate some tools like this. So now that is actually, leader follower type of control, and we call this method in the bio-artificial synergies. Now, the other side is spontaneous independent controls, and the people try to put many sensors and wearable sensors at many parts of the body, including foot switch and then shoulder switches, so that it not interfere with the main task, but it can also control the extra limbs. Now, interesting point is that looking at the whole body, hands are most dexterous part. So if these hands are available, you would actually use the joysticks or switches to control it. But those actually most dexterous hands are actually usually busy performing the main task, right? However, if you think a bit more carefully, holding this, grinding tools, of course, the total forces created by 10 fingers must satisfy certain actually value, but distribution of finger forces, because you have 10 fingers, although the sum is fixed, but each distribution, fingers distributions may be arbitrary, so that actually gives you the chance to create some code to send to the robot. So here's the fingertip the sensor is actually implemented. And you don't have to actually open detach from it, but just changing pressure, you can actually send some commands. What we do is basically we first ask the human subject to show the many finger the holding operations, and it turns out that the first few components represent again the most of the data, leaving so this is the 10 finger, the 10 dimensional space beyond this point and unused for performing the primary task, that is holding some tools. So that said, you can use this space for sending some coded signals to the robot. That's actually we call the null-space communications. So pushing this one, SuperLimb up, this one SuperLimb down, so that kind of code can be created. So this Hanjun is wearing the simple robot, and actually he's also wearing the glove there, so he can control this robot with this, although both of his hands are busy holding this box. But he can actually controlling this, right? So it can go, and he can, going to the elevator halls. Oops, elevator's coming. I do not recommend this, but you can do that. Yeah.
Hey, Hanjun! It's been so long, man.
So that party.
You are?
I suggest that this may be a good costume for Halloween days, and if you wear that and moving around and moving stuff, but don't do it for your kids. Now, more serious side, control of SuperLimb, it's not just a sensor design in that kind of a program. We face much more profound scientific issues. So, to a large extent, SuperLimb is to perform some multiple tasking, right? So maybe two of them are SuperLimbs, but bringing the foreign object attached to the human body. Can the brain support that SuperLimbs? Can a human control the natural limbs on arms and SuperLimbs simultaneously? would it be some kind of a cognitive limit to it? And if you look at the brain, all the places are kind of busy, the body image of this stuff and occupy the whole part of the cortex. Is there any room for the SuperLimbs to create its own, brain, image over here? And however, if we do the right things, and the additional arms are basically, SuperLimbs are nicely mapped out in here, would it be possible that the wearer get to perceive the SuperLimb as a part of his or her body, extension of the body? How we can make that happen? So, Federico Parietti did the first human subject test. What he did was he actually, built the two simple 1DOF, SuperLimbs here and here. And also his arms have to follow these target stuff simultaneously. So in this experiment, so the human subject is actually, actually pointing their arms along this marker direction to this one and this. And this is the SuperLimbs, and pointing at this guy, this marker. And this one is a little hard to see, but the black ones are pointing at this one. And they change the locations, simultaneously. And, you have to make sure this one is actually pointing at certain directions, and as such. If you see this, the robot right arms, the robot left arms, the human right and the left arms, they are basically approximately, following this, tracking this, that's reasonably. He used the EMG, in particular measuring the muscle activities at the abdominal part, and which is not used for the arm motion, so we can do it independently. And an interesting point is that, so we get the 4 measurements, right? Two robot arms and the 2 human arms. And this is the chart where 2 of them are plotted on a horizontal and vertical axis. This is the right human arm and left human arm, and the trajectory is plotted over here. Now, interestingly, you see the kind of oblique trajectories mostly in here and here, indicating that the left arm, the right arms moved simultaneously. And do the same thing for 2 robot arms, the right and the left. It's not clear this, but it includes some of the significant oblique direction of motion, meaning that the 2 robot arms occasionally move simultaneously. However, if you combine 1 human arm and 1 robot arm, putting this one and x and y axis, the trajectory is mostly horizontal or vertical, indicating that the 2 robot and then the human arms do not have to work simultaneously. So all combinations, we confirm that they do not work simultaneously. So 2 robot arms and the natural arms do not move at the same time. The human look at the his own arms and actually robot arms back and forth. It's basically attention allocation problem and being distracted by the other part. So they do some kind of time sharing. Now, visual feedback is at this time the high-level cognitive control that dominated this experiment, and hands are controlled with the visual observation, but not just the visual feedback. We have some haptic feedback. This is the interesting part. So this is the robot on the shoulder. The robot is holding this part when he working on this to fix it. The force borne by this SuperLimbs transmitted to the wearer's shoulder over here. So wearer recognizes and also confirm that the robot is really bearing the load and holding this. The robot is not the one sitting on the floor, but it's attached to the body. So we have an inherent, haptic feedback, acting on the body. So in some way, this direct haptic feedback may reduce the visual cognitive load of the human, And the SuperLimb and have this unique feature that feedback that can be exploited. So Jacob Guggenheim, he looked into visual and haptic feedback in depth and how they work together. And his experiment is actually first he developed a simple SuperLimb over here, which is actually contacting the tables and apply some force. Thereby, it received the reaction force, and that's transmitted to here. And he designed some simple attachment plate. Through that, the human actually sense some actually the force and torque being generated here. Well, the back is the most insensitive part, but he found that the robot and the human can control this force feedback loop through this haptic feedback. But the interesting point is that not only that the haptic control, but the human subject is instructed to respond to a visual cues over here. It's basically a visual task. These letters are shown up in here randomly. And whenever the white letter shows up, he has to push the one button on the game console. The other game console the switches is to adjust this, regulate this contact force through haptic feedback. Now, the point is that and after having about 10 plus human subject, this is the final result. And this column, actually no haptic works, only visual task. And then this actually column shows that the haptic task alone. And this column shows the haptic and the visual task concurrent simultaneous stuff. And this is to show the kind of violin, the structure, the distributions, and then the kind of performance is evaluated with respect to root mean square. We have to regulate the force. And then there's no statistically significant difference between these two cases, even though you actually impose additional visual task. Most of the human subject did equally good work with the haptic alone task. The visual task a little bit degrade as you put the the haptic task, but the difference is not statistically significant. The another situation is that shown here, he is really actually watching this his own fingers and screwdrivers, but because of this haptic feedback, he is kind of aware, at least aware of the fact that the robot is holding this actually plate good through this haptic feedback. So to examine this more quantitatively, we developed that actually we use that in the same haptic SuperLimb systems. At this time, it creates some kind of the torque over here, which should be sensed by this the human subject, and whether it actually detects the right, this one at the right timing, and which type of, going down or going up, and which type of one is to be reported. It turns out that this is again both the haptic and the visual distraction task and performed at the same time, and it is haptic alone. There's no significant difference between the two. This one's also not so much significant. So we can conclude that there's no statistically meaningful difference in performance between simultaneous haptic plus visual task versus haptic task alone. So this is good news for us because visual and haptic feedback can coexist and actually function simultaneously. So when you actually multitasking stuff, mostly primary task will be done by natural arms and monitored by the visions. And actually, SuperLimb is mostly supportive work. And that's in the secondary task. Visual attention is not going there, but the haptics is always actually acting in that to see whether there's something going wrong. Let me talk about the one more interesting stuff. This one is actually the DOE project. So this is actually radioactive waste management systems, and the workers there have to actually wear very heavy life protection gear, personal protection gear. It includes the oxygen tanks and the air conditioners. If you put everything, it's more than the 30 kilograms, so 60 pounds. It's a very heavy load working there for a long time. So we built the robot that is to reduce the load, and all life-saving equipment is carried here, work together with the humans. So it turns out the two legs and then the two robot legs have to work together when it's walking. And this turns out to be an interesting problem because, if both, two pairs of biped legs are actually, coming from animals, its central nerve systems create the beautiful coordination between rear legs and front legs. Likewise, the big dogs have a nice computer to coordinate this, but we're dealing with some half animals and half robot and half human, half robot systems. We first tried to combine this rigidly, just like exoskeleton, the people doing that. It turns out that's not a good idea. And in fact, if you connect these with some compliance and a dashboard, we created a very interesting behavior. If you look at the animals' work, and actually, front legs and number 1, 2, the rear legs and 3, 4, it goes 1, 4, 2, 3, 1, 4, 2, 3. That's actually gait, right? When you're walking, because that maximizes the stability, static stability. Now, interestingly, as you model this, two independent biped systems and connect them through dashboard and springs, it actually initially it's an arbitrary phase, but after somewhere going this, actually 4 legs and then rear legs are 90 degrees out of phase, which is exactly animals do. So these two are not connected through active control, but just possibly connecting this, we can actually do interesting jobs. And so now Dan Gonzalez, he did a very interesting experiment. This is actually two set of rimless wheels. Both are connected through just a passive springs and a dashboard. He started with some arbitrary initial conditions, let it go. Interestingly, at the end, these two are exactly 90 degrees out of phase, or 25% of the cycle, the stuff. So initially, then he measured this, it's going there. There's no active controls, communication between this part and this part, but dynamically interacting through the springs and dashboard, it arrives at the right phase, which is wonderful, and that is to be the very stable locomotions. Of course, we did some analysis, and this is the Paincare return map. That's kind of standard techniques in the leg locomotion community, and we checked whether or not actually these two rimless wheels converge to the certain desired phase lag, and we accomplished that for a certain combinations of damper and the spring constant. Yes, the systems converge to that one firmly. Now, back to a little bit, actuator stories. We started with the direct drive, right? So, this wearable, robot and limbless, SuperLimb, need new actuator technologies, and desperately we need to have the breakthrough in actuators. So, this is a case we'll build the wearable canes for supporting the elderly people. Yeah, before I retire, I need this kind of a device. So, when those people are weak and they have a hard time to stand up from the seated locations, we need someone to lift up. And this requires almost 240 pounds of payload that must be lifted. At the same time, the role of this guy is to prevent the falling. Falling is very dangerous. So, what we'd like to do is to relocate these canes to the appropriate locations very quickly to catch a fall. So for this guy, you have to lift this one, move to the next point, and then quickly go down. As soon as you landed on here, you have to bear 240 pounds of load. So it turns out that if you plot it in the speed, torque characteristics curve, one actually you use these motors in two extreme conditions. One is that you have to generate a high torque, but at a very low speed, slow speed, or you have to move it quickly through the space that's actually small. Actually, the torque is needed. So how you can meet this? If you just pick the one motor to cover these two extreme cases, you have to pick the gigantic motor, and whose actually output power is maximum in the mid range. This is at least used regions. So actual power coming out of this is just this much or this much. Very bad usage. So we recently solved this problem by combining two tiny motors. It's called the dual motor design. And one motor is near direct drive. It's actually in high speed range, and the other motor is actually with high gear reductions and geared motor. It's called the torque boosters. So by combining this, we get the much more efficient operations. We can do two ways of doing this: dual motor, dual speed actuators. One is adding two speeds. The other is adding two torques. Adding two speeds, typically we use the differential gears. So, high gears, high torques motors comes in this way. And here's actually direct drive, going to this. For high speed motions, this one is to take the most of the velocity here. But a high torques case, this is to play the major role, but this has to bear the same torque. And then this one cannot actually bear the torque, so we have to use a brake or use the non-backdrivable gears such as the worm gear, which is very bad in the efficiency. So this is one design, and the other design is to add the two torques together. This is actually interesting too. Let me start with the adding two stuff. So it moves very quickly, and then push the very heavy stuff. And as soon as it hit, the brake is on and it's changed the mode, and it becomes 20 times bigger torque being generated in that. This one too, once hit it, switch back, and large torque comes out. The other way is to use the different architecture, torque superposition. So in this case, because the previous one's good, but still need to use the brake, and that's not good, and then a little bit bulkier. So we try to minimize the mechanisms, and so our solution was just putting together. So this is direct drive, and this guy is to just attach, connected to this. We don't want to use any mechanical switches and on and off brakes, and we don't want to use that. So the problem is that when actually high speed mode, this is spinning at high speed, and this one cannot catch up with it because it's high gear reductions, and if you ought to rotate it, it creates a large back EMF voltage. So in a sense, this works as the kind of generator, eating up the power from this, which you don't want to have. So the idea is that we actually make not the mechanical switches, but electronically switches. We basically, disconnect these motors from drive systems. So let it go. That is a simple idea. And this is the recent result. So, actually, so this lamp is on when actually, torque boosters are engaged. So, when accelerating, large torque is needed, still velocity is low, it's actually, torque booster is working. But after moving here, it's basically, torque booster is, electronically disconnected. John Bell's, developed the time optimal controls in doing this. So in here, just a single motors go up and around. It takes a long time. But on a dual motor, with this switch off mechanism going up beyond this limit, if this travel distance is further, it's going higher, and come back, right? And coming back is along this trajectory, which is very quick deceleration because torque booster is engaged again. That's actually quickly stop it, so we can actually shorten the the time. If we do not switch, it takes more time. Okay, and the top speed doesn't go up beyond this limit. What time is it? Okay. Just 2 more minutes, okay?
You're very interested.
Okay. I had to show this at the end, but this is really actually, how to say, the crazy science, how to say. But we've been working on it. Use of live cells as components of a robot. In particular, we are interested in the cardiac muscles or skeletal muscles. Use that as actuators. Vincent changed, he built this kind of stuff some time ago. But in general, about the last 15 years or so, many people, including Kit Parker at Harvard, they try to use the cardiac muscles and use that one as the actuators. Many interesting features you can enjoy that you can't get the traditional dry engineering. And these stuff and directly convert the chemical energy to mechanical energy, and it's a self-assembly and a mass-producible, and then fault-tolerant design, and reproducible, and self-repair, regenerative stuff, and on top of it, battery submerged. If you try to build some small robot, all the way the difficult point is how you power that and how you put the cables from the battery to there. But these animals are basically, I would say the robots. Is it robots or animals? The robots. It basically submerged in the media, so nutrients and oxygens are actually transported through that. Of course, you have to use some vascular network. Well, you think that the live cells are very totally different kinds of species. It's hard to observe in the traditional engineering, but in fact, it's not. We use a lot of mechanical engineering type of techniques, including the molding. And we use a lot of fine molding techniques. Mold that, and actually these are cardiac muscles, and so they are spontaneously contracting. It's not the rubber band, but it's actually a muscle stuff, so it moves in this way. So that is something already existing. However, what is how we really control that and coordinate that? That's very important. So traditional method is use the electric stimuli. So putting in some electrode and then stimulate this. One problem is that while in a wet environment, the current is flowing unexpectedly. So you can't pinpoint which particular muscle to activate, right? And also, it's relatively slow, kinetics and poor, reversibility, and most importantly, it's very much invasive. On the other hand, we successfully accomplished the optogenetic controls. Instead of electric stimuli, we shine the lights on the muscles where it is changed to having a different behavior, so that it is to respond to lights. So no mechanical contacts and wireless communication, minimally invasive, and actually temporarily very precise. And also important is that spatial resolution is extremely high, and a multi-DOF motion can be generated. My postdoc, Selman Sakar, did it first back in 2012 for skeletal muscle. You know that the cardiac muscles shrinks, contract spontaneously, but the skeletal muscles you have to provide the stimuli from outside, right? So he used the optogenetics, and say in this case, 3 muscle strips sitting here. If you expose 3 of them to distant light, all 3 shrinks. If you just shine the light only over this part, only this strip is to contract. So in this case, first this blue light is all 3 muscle strips contracted, and putting this, only this guy is to contract, and other side just this guy to contract. So the spatial resolution is wonderful. We can actually contract each specific muscle strip individually. So extending this guide, what I'm dreaming about is that if you want to make the small robots, you used to put the say 10 degrees of freedom in the area that less than just a millimeter. There's no engineered actuator that you can do that, but muscle actuators, yes. There's a potential, you can do that. And also, if you make this one out of IPS, take the cell from you and put into that, putting your body and then fixing something, and after that it's biodegradable and then nothing harmful in that. So that is something interesting in the future view. So to summarize this, we talk about human. SuperLimb. Human can possess the 5th and the 6th limbs, and SuperLimb. Well, practically useful, I would say. And we showed the robot on the shoulder and the mantis bot and the wearable fingers. And controls is actually more challenging. We look at the use of the narrow space communications, and they do. Vision should not be overloaded, but these robots are attached to the human body, so we can actually exploit the inherent haptic feedbacks. And that inherent haptic feedbacks and vision systems go very well side by side. So the main robot, the main natural arms are supervised by visions, but support SuperLimb can be observed and monitored by the haptic sense. Dual motors is very promising. That's actually today's technologies. But if you extend your scope and something in the future, well, the biomaterials can be used as the components of the robots. Who did it? This is my group. We went out for dinner after I got some new funding. So we go to the everyone in the chapel. And this is my list of the sponsors and DOE and then NSF grants and so forth. Thank you very much.
That was very inspiring. Are there any questions, thoughts, comments? I didn't understand the dual actuator. Don't you have to mechanically disconnect the geared motor? Otherwise, its friction and its high motor inertia will cause problems.
Not much. So that's actually real mechanical engineering kicks in. Well, torque booster side, you don't have to worry about the zero backlash, right? Well, the friction that happens because you carry it in a backlash. Right, so we have very, very relaxed design conditions, and yeah, so we're connecting that all the time. But I know we can manage that.
I'm skeptical, but
Yeah, has any work been done into looking at how people with supernumerary limbs and fingers have been perceived by other people? So like, let's say you walk into a room, or you're elderly, and you have like 2 canes attached by your hip.
Right.
How is that how is that taken to be?
Yeah, that's why I'm suggesting you to wear that for the Halloween days and see how the people react to it. But seriously, well, it's actually tech nerd type of stuff as of now. But we're looking at the specific task, like aircraft manufacturing people. They do need some support, otherwise they got the trouble in here and there, right? So for starting with some more specific needs, for that, it needs some time that the society, the people accept this and feeling comfortable with it. But we're the group and doing all the kind of weird things for every time. So needing some time, but I know it is quite conceivable that our body is not designed well for certain tasks. So, and we like to extend our abilities. So it works in that way.
Let me just point out, Jimmy Carter has fallen down twice in the last week, and the second time he broke his pelvis, or fractured his pelvis. For older adults, that's a very compelling reason to look weird. And by the time this stuff is practical, you'll be the older and you'll have grown up in this era of smartphones and weird stuff. And you'll be totally happy. You'll be Doc. It'll be great. Over there, Keith.
What are some practical concerns you've encountered with the mechanical interface between the limbs and the human body?
Mechanical interface? Oh yeah, that's a good question. So haptics is actually, things we have to do very carefully. And then what is actually right, distributions of the force sensed here, transmitted here, how that wanted to be distributed in here, right? So, I graduated, Jacob Guggenheim, but before he reached that research, yet, but he wants to graduate. So it's actually, we didn't do much, but he found that many, kind of design guidelines and exist. And this is actually, kind of a, cross-disciplinary studies with, robotics and, haptics in the community, biomechanics community.
Well, go ahead.
On the HRI studies you were doing, where you were looking at human factors of how fast people could do different tasks, different stimuli. It seems to me like there's kind of two different parts. There's the transient when they're first learning it, and then there's the steady state. And it seemed like you kind of lumped those together in this talk. Can you comment on that distinction a little more?
Yeah, we lacking in the long-term effect studies, well, many reasons. It's a little difficult to do, experimentally, rigorously. So we, in a sense, cut off, and actually, this job, we did it for, about 3-4 days. And so we did observe the learning curve, which is very interesting. But more concern is that the kind of negative effect of long-term use of this. So just like, some bio firms, TV commercials, the people are showing the very cheerful things, but an announcement said that there's a kind of serious illness and such. This is exactly the case. It's good for doing this, daytime, but I don't know if the person is using this in, 8 hours and daily, and what happened after midnight, he still feels that there's something moving in this, kind of a phantom that comes out, and I have no idea what is the long-term effect. Did I answer your question?
So I'm going to ask a question just to be a little controversial, just for fun. I don't mean any disrespect. So it's two parts. So the first one is, for your supernumerary limbs, they're always anthropomorphic. So why do they have to be anthropomorphic?
Oh, yeah, it doesn't have to be. One is actually this, cane. First, the cane is a sliding joint. But interestingly, that's not purely engineering viewpoint. It's not effective. This articulated joint is more effective. That we found. But even though we take the articulated ones, kind of proportion between upper and the lower limbs, tends to be different from the human limbs, and depending on what you want to do with it. So I don't think I can draw the clear line between the two.
But they still look human-ish, whereas like an adept robot is definitely not human-ish.
Right. So one is actually, perhaps you are guiding me to this point, kind of, technology acceptance, kind of a mental issues, So, people feel comfortable with it, and then the motion should be predictable. As in the case of other part of the body, it should be predictable. So maybe I was biased or influenced by that notions, but I know this is the kind of point that we have to do more rigorous work.
Thank you.
You had a follow-up question?
No, I'll pass it.
To Kale.
I heard in BMI brain interface for monkey to pick up a thing. And then in the beginning, he wants to move, but since the hand is bind, he struggles. But eventually he learns that he doesn't need to move to get the award. Only he needs to think, number one. Number two, somebody actually did some research. Human brain actually has a much more multitasking capability. So than we think. So if we combine the two, will it be possible to have a brain interface so that the human actually can control more than 2 or 3 or 4, even 5 limbs by just thinking?
Yeah, that's possible. Andy Schwartz, the next door at the University of Pittsburgh, is one of the leaders in doing that, right? I, to some extent believe, to some extent I don't believe, for numerous, specific engineering issues involved. But I know pushing our time frame to, significant, period, that's really conceivable. But more interesting stuff, Takeo, is that, our human brain is very, plastic. So we can adapt it to that in many ways. So whether this kind of limb can be actually nicely mapped in here, and also interesting that this is not the robot sitting on the floor. It has haptic feedback all the time. And we found in the literature that the visual stimuli signal lines and haptic lines for some class of tasks going to the same place in the cortex. Meaning that there's 2 pathways going there. So that is actually, some are actually repressed by haptics, some are, visions, and actually integrated these 2 things make that the case. So this one suggests us, how we can actually incorporate the, supernumerary limbs in such a way that is we exploit the brain structure. So there are not a lot of things that we have to consider. What is actually so this is not the kind of stuff being discussed in the robotics, but have to go into the cognitive brain and cognitive science. Your home department, Chris, have to understand that the structured brain, more rigorously, and map that one to our robotics domain. How these, foreign, robotic and animals to be incorporated into our body.
Yeah. And so how did you use Synergies for controlling your SuperLimb? Did you only use them, or do you use that as a feed forward?
Yeah, mostly a feed forward. Well, constantly actually, recalculating and doing that. We did not actually initially, try to study the, synergies, but as a result of the data analysis, it came out almost the same structure as in the case of the biological real, synergies. But, our kind of interesting point is that even though you extend it to a SuperLimbs, extend the number of joints, we have very similar structure as in the case of biological synergies. We call that bio-artificial synergies.
Yeah, go ahead.
So when you run your experiments, how do you ensure that the robot does not hurt your steady
He doesn't care.
I do care the students, I do care. Well, at MIT, we have a very rigorous, IRB, internal review, board, and so every single change we make to our human subject test, we had to write a bunch of documents and get approval, which is almost, it's not a city, but I know it's very much, humans are protected by that, right?
But the question really is, so even when we run any robot, it never runs the way we want it to run on the first try.
Oh, sure. Yeah. Now, our lab, we have a kind of a collection of tips, the do's and don'ts. Yeah, so that's, we really have to, satisfy. But, IRB, when you put together the documents to get the IRB, you have to, they check the other stuff. For instance, putting the robot on the shoulder, this sounds very, dangerous, right? And on the other hand, this guy is safer. If the robot here, relative location that may be arbitrary, right? But the thing here, the, relative location of the robot to the human is fixed. So we can actually, it won't hit the head and this area. So in a sense, it's actually safer.
Okay, let me actually cut things off because we have phase 2 of this morning, which is we want to show off the CMU Direct Drive Arm 1 that was recovered from the warehouse. I have to say we have not cleaned it. That is very controversial in the museum world as to whether you clean things or not. We also have on display the CMU Direct Drive Arm number 2. And I put up there a standard geared robot that you can grab and sort of pull around and feel the difference between a geared robot, and I urge you to push the blue CMU Direct Drive 2 robot and see how easily it moves. I believe in this museum stuff that part of the point of doing this at CMU is to put no barriers between you and the object. So that you guys are all, or most of you are roboticists, you want to touch things, look at it, figure out what kludges are in it. There are plenty. The CMU Direct Drive Arm 1 is older than most of you in this room. And has a little bit of arthritis, so it doesn't have anywhere nearly the smooth movement of the blue CMU Direct Drive Arm 2, but feel free to touch it, push it around, whatever. Okay, so it's going to take us about 5 minutes to clean up here, but hopefully we'll meet you all upstairs in the 4th floor hallway right before the bridge to Weed. And there'll be a dramatic unveiling, and I believe we have a photographer for the event somewhere. It'll be very exciting.